be talking about notes 2.1. Oh, I didn't give you your gold sheet. So as you're dragging this down, I'll give you your gold sheet. You do have a homework assignment today, and you do have a quiz tomorrow. I know one class had asked me if there was going to be a quiz this week, and I didn't know because Mrs. Holman and I had not discussed it. Then we discussed it, decided we love quadratic so much, and you probably do too, that you would appreciate a quiz tomorrow. Quadratic, this note. Just this note. No, there's two questions. Why is it? Because there's a lot of questions in those two questions. I wouldn't give you anything you couldn't handle. So it's only over what we're doing today. Okay, so we're going to be talking about quadratic and functions and models today, and we're specifically going to be working with something called standard form, which is a little bit different than the standard form that you learn in Algebra 2, but it's a form that you're familiar with. So we'll talk about that when we get there. To go ahead and start, I just really quickly, and I'm not going to stay here long, just chat about polynomial functions. Because quadratics are a subset of the polynomials. Polynomials are functions that are classified by their degree. Does anybody remember in the polynomial what is the degree? Maddie? The exponent? Which exponent? The highest exponent. Thank you. Okay. So classified by degree, which would be the highest exponent. So there are some that you have special names for, like if your highest exponent is 0, that's a constant function because x to the 0 simplifies to just equal 1. There is no variable. If there's no variable, then you're constant. Okay, so that's a constant function. If you have a degree of 1, then you're linear. 2 is quadratic, so that's our quadratic function, degree 2. Okay, and you guys said that in the warm-up, so you already knew that. 3 is cubic. Does anybody remember the name for a 4th degree polynomial? Quartic, and then maybe you did 5th degree was quintic. After that, you just say like 6th degree, 7th degree, so on and so on. But we want to focus today on quadratic functions, degree 2, so we're going to be looking at things that have x squared somewhere in them. That's their highest exponent. Eventually, in sections 2, 3, and 2, 5, we'll get into the polynomials. So we'll go back and review polynomials like you did in Algebra 2. All right. Again, there's a lot of stuff you guys already know about quadratics. So this part of the notes is like you pick and choose what you want to add into your own notes. And really that warm-up was a great review of things that you already know about quadratics. So we know that quadratics are parabolas. Somebody said that in our warm-up. And a parabola or a quadratic function will either open up or down. Do you remember how to tell if it opens up or down? Elena? Yeah, a negative in the front of the function will make it open down. You had a couple of forms last year, like they might have looked like this. A times x minus h quantity squared plus k. Or we also had a form ax squared plus bx plus c. And in both of those you have an a. If the thing in front of the x squared is positive or negative, that determines whether it opens up or down. There's a vertex point. So remember the vertex, and I don't think we wrote down the vertex on the warm-up, but we talked about going right 3 and up 4, so the vertex would have been at 4, 3. Oh, maybe we did talk about the vertex. Yeah, we did talk about the vertex. So that's HK. Remember, with the H, you have to be really careful. In this form, H has a negative in front of it, so it looks like the opposite. If you were to drop in a positive 3, it would look like x minus 3. So when you take H out, it looks like the opposite. And that also determines your max and min. So depending on whether your graph is opening up or down, you'll have a max or min. And I got those flip-flops. So a graph that opens down has a maximum, and a graph that opens up has a minimum. That's a really important point if we're talking about like modeling with quadratics. So quadratics can be used to model falling objects, projectiles, jumping, height versus time, or maybe even height versus horizontal distance. And so we might be curious, like, what's the highest point, right? Axis of symmetry, you guys came up with this, so nice job. I'm going to abbreviate that AOS. And then on your reflections on your test, some people talked about, like things they like or dislike, and I'm not surprised I'm with you on this. It can be hard to take all the nitpicky things in pre-calculus, right? Got to write intercepts as ordered pairs. Got to write this as the equation of the line. Axis of symmetry is another one of those. Axis means line, so when you give me an axis of symmetry, it should be the vertical line x equals h. If you just write 4, it's not a line. Okay, so you lose a point for that. So know that that's going to be one of those nitpicky things. I feel you on it, but what can we do? We want to be better. And then also remember x-intercepts. X-intercepts are like the zeros. Emma, did you have a question or are you just stretching? Oh, okay. I thought you were like your hand was so tired from me like not noticing you. X-intercepts are zeros. And you can find x-intercepts by setting y equal to 0 and then solving for x. Let's just have a real quick discussion or recall here. What's the most amount of x-intercepts a quadratic could have? 2. So imagine the u, maybe it's opening up and it's sitting below the x-axis, so then it's going to cross the x-axis twice. What's the least number of x-intercepts a quadratic could have? 0, because maybe that u is sitting above the x-axis and still opening up, and so it never crosses the x-axis. If you solved for your zeros, you would find an I in there, an imaginary number when you square root a negative, so then you have no x-intercepts. In between 2 and 0 is the number 1. Is it possible for a quadratic to have 1 x-intercept? Okay, describe to me what that quadratic would look like. Vertex is on the x-axis. So maybe it's sitting on the x-axis and opening up. Maybe it's opening down and it just peaks at the x-axis and turns around. Now, technically there are 2 zeros right there. It's called a double root, or it has multiplicity. It's the same thing twice. But we would say in terms of x-intercepts that it only has 1 x-intercept. Okay, good. Okay, now, some problems on your homework will ask you to graph and identify some of those special characteristics on the quadratic. So if you're being asked to graph a quadratic for me in this section, I'm basically going to say use your transformations. You don't need to make a table of values with 10 values. I think that's a waste of your time. We know about transformations, so we'll use them. Okay. You guys did a really nice job on the test, on the questions like 9 and 10, where you named transformations and you drew the graphs and you did the stretches and stuff like that. So we want to continue that. Think about always, if you're graphing using transformations, even though you're not creating a table of values, use what you know about the parent function to get maybe 1 or 2 extra points. Okay. So we're going to sketch a graph, and then we're going to label the vertex, axis of symmetry, and x-intercepts for this function. F of x equals the quantity x minus 1 squared minus 3. Okay, so before I even start to graph, I'll probably start with what is my vertex? Give me my vertex. Anyone? 1, negative 3. Very good. So I'm going to go right 1 and down 3. Okay, there's my vertex. So I'm now graphing with the transformations. The transformation of the vertex from the origin to the point 1, negative 3. Might look at my A value, or like if I have a vertical stretch or shrink or a reflection out in front. Nothing's there, so it's going to follow the same pattern that the parent graph would follow, which would be normally from the origin, you have 2 points on either side, like up 1, right 1, up 1, left 1. Okay, so I can mark those points. And then if you want any additional points, you can use the next set, which is like the, when you put in 2 for f of x equals x squared, you get 4. So you would go up 4 and right 2. So you have a point over here, and up 4 and left 2, and a point over there. I don't expect to see that many points. I'm just showing you. Some people put extra points if you want to know how to get those extra points. What's my axis of symmetry? X equals 1. Thank you for writing it as the equation of a vertical line. I appreciate that. Okay, we can see that right here at x equals 1. Okay. The graph would fold onto itself. The two arms are reflections of each other. So we've got a sketch of the graph. We've labeled the vertex. We labeled the axis of symmetry. The other thing we need to do is label the x-intercepts. Now, if you can find the x-intercepts from your graph, cool. Write them down as ordered pairs. In this particular example, where it's crossing the x-axis is not clear to me. I could estimate it, but I want an exact answer. So if you can't tell where it's crossing the x-axis, then use algebra. So we're going to set f of x equal to 0. Also on your homework, if you decide that there is no x-intercept, then just write none. Don't do any work, right? If your picture doesn't look like it's going to cross the x-axis, I don't expect you to find them if they're imaginary. Add 3 to both sides. Square root to solve. I'll move this up here so everybody can see. This is where we got to be really careful to get 2 x-intercepts. When we square it to solve, we have to add a plus or minus. Excellent. So it's going to be plus or minus square root 3 equals x minus 1. And then finally add 1 to both sides. So 1 plus or minus the square root of 3 equals x. And I prefer, or I should say rather I want, exact answers. So square root of 3, I'm okay with that. Please don't give me 1 plus 1.73, which is 2.73. I want it exact. So I could write my x-intercepts 1 plus or minus the square root of 3, comma 0. Dylan.
So is it alright if we wrote down and said 1 plus 5.30 and then
Yes, you could write them separately. Because there are 2 x-intercepts there, right? So if you don't recognize that, maybe separate them. Now, if for your own purposes you want to estimate them as decimals and figure out what they are, to like, does that really make sense? You could use your calculator on your homework, or just estimate the square root of 3. I know it's 1.73, but you would at least know it's between 1 and 2. The square root of 1 and the square root of 4. But if you added that, that would be like 1 plus 1.73, which would be 2.73. Doesn't it look like I'm crossing at about 2.73? Yeah, so like I'm pretty well convinced I've got the right x-intercept. But I'm really looking for the x-intercepts as an ordered pair with an exact answer. Does anybody have any questions or concerns about what they might be asked to do in those questions? Okay, now, we are going to call that form that we're working with, it's sort of like the transformational form where you can see A, H, and K. We're going to call it what the book calls it, which is standard form. This is not what you called standard form in algebra. So last year, standard form was the one that was ax squared plus bx plus c. So that might be, for some of us who learn what things are called, that might be a tricky switch for us. And it's tricky for me because I teach algebra 2, so I'm calling it one thing in pre-calc and another thing in algebra 2. This is what you called last year. It's your old vertex form. I actually like calling it vertex form because it's called vertex form. The vertex is staring at you in the face. HK. Just pull it out of the equation, right? So nice. I love it. The other one, not so much. So that's your old vertex form. There are going to be some problems on your homework where they're going to ask you to take something that's not in not in this standard form, and write it in standard form. So that's where we're going to go next. We're going to practice that. That's probably the toughest part of today. So here's an example. This is the directions in the book. Write the quadratic function in standard form. Sketch its graph. Identify its vertex, its axis of symmetry, and x-intercepts. The second part of that is what we just did. Graph it with the transformations. label the vertex and axis symmetry as ordered pair and equation of a line, and then if you need to, solve for x-intercepts and write as ordered pairs. We're going to focus on this first part, write in standard form. I can only graph so many quadratics before half the class falls. So we're going to focus on the rewrite. Okay, so notice that this one has x squared and x terms. We want to make it look like this, where we have really in the equation a single x that's inside of a binomial that's being squared. We're just going to put this out there. Does anybody remember how you did this in Algebra 2? Because you did rewrite things in vertex form in Algebra 2. No? You think you got an idea? Okay. If you factor this, then that turns into intercept form. And intercept form, because, you know, if you set your factors equal to 0, you get your x-intercepts. That's why it's called intercept form, because your intercepts are staring at you in the face. So factoring, though, does have a part to play in this, but we won't straight up factor that equation. Okay, Dylan? Yes, that would be a roundabout way of doing it, but we are not going to do it that way. We are going to do it a different way, but I agree that that would be a method that works. I'm going to teach you something different. Anybody else? Your thoughts? Thank you. Complete the square. Everybody's favorite. It's so cool. It gave us the quadratic formula. Complete the square. It's amazing. Okay, we're going to rewrite it by completing the square. So, in order to complete the square, you basically want to have an x squared term and an x term. And you complete the square for those two terms. So that plus 5, it's part of the equation, but we don't really need it. So I like to move it to the other side. It's like putting it away for storage. I'll bring it back later, but I just don't want it over there because it's confusing me right now. So let's subtract 5 from both sides. f of x minus 5 equals x squared minus 6x. We're going to complete the square for x squared minus 6x. Right now there are only 2 terms, but when you complete the square, you're creating a perfect square trinomial, which means it has 3 terms and you're finding the constant. Perfect square trinomial is just like a perfect square number. Why is 25 considered a perfect square? Because 5 times 5 is 25, right? Because 2 numbers or 1 number multiplies by itself. So a perfect square trinomial is a trinomial that when factored has the same 2 factors. And then we can write them as the x minus h squared. They're being multiplied. So does anybody else remember how to complete the square? Campbell?
I said you take 3 halves of the b term, and then I don't know what to do from there.
Okay, Liam?
Don't you take half of b and square it and add to both sides?
Yes. Half. Did you say 3 halves or half?
I said 3 halves.
It is half. It is half. Okay, so let's write this down if we need to in the margins of our notebook. Complete the square. You are saying B, that's totally fine. I'm just going to say half of middle term, but you can say B if you want. And then square it. Those are bullet points, not negatives. So I would take half of what's going to be the middle term, which is -6. Half of -6 is -3. And then square it. So I'm going to add 9. Now, think about why 9 is the number that completes the square. What's the definition of a perfect square trinomial? If I were to factor this trinomial, what are factors of 9 to add to make -6? 3 and 3 if they're both negative. So that's considered a perfect square trinomial because the two factors are exactly alike, x minus 3 times x minus 3. Which I can then write on the next line. Oh wait, before I do that, I better talk about this. I had an equation in black, right? And then we completed the square together and put a plus 9. So on that left side, I just added 9. What I have to do? Add 9 to the other side. So don't forget that you have to keep your equation even. You're still balancing things. So this is f of x plus 4 equals, and now I can rewrite this, which would factor as x minus 3 times x minus 3 as x minus 3 quantity squared. And then the last step is subtract that 4, bring that back. Okay. Could you now, yes? Oh, yeah. Subtract 4. Oops. Could you now tell me the vertex? 3, negative 4. Could you give me the axis of symmetry? X equals 3. Could you graph it using transformations? Yes. Could you find the x-intercepts on the graph or via algebra? Yes. So then you would do all those things. But we're not going to do all those things because we want to do a harder one. Yes. I saw Nate looking at me thinking, Miss Cronky, that one's so easy. Why would you even bore me with
You
that?
read my mind.
I know.
Let's go.
Nate was ready to fall asleep. That was so boring and easy. Oh my
Come
god.
on, that was never.
All right, f of x equals 1/4 x squared minus 2x minus 12. Okay, if we were rewriting this in the new standard form, it would work the same way. We don't want that constant over there, right? So first thing is add 12 to both sides. Now we're running into a trouble spot. You're not allowed to complete the square if the a value, the coefficient to x squared, is anything other than positive 1. So if there's a number there, if there's a negative there, that thing has to be factored out of all the x terms first. Since there's a 1/4 in front of x squared, I'm going to factor out 1/4. So factor out whatever is in front of x squared. Now I'm showing you this fraction example because every now and then people get confused with the fraction. Dylan. You can multiply both sides by 4 and then in the end you'll have to divide by 4. Like you should still have the 1/4 as an a value. I don't do that. So I'm going to show you my way. But if you want to do it your way and get the same answer, that's fine. When you factor out 1/4, it's like dividing the terms by 1/4. So like 1/4 x squared divided by 1/4 is just x squared, which is what you want, right? And then be really careful with factoring out a fraction. If you're factoring out 1/4 from -2, it's like -2 divided by 1/4. I'm going to write that over in the margins of my paper. If you divide by 1/4, what are you really doing? Multiplying by 4. So this will be -2 times 4, which is -8x. I can't tell you how many 1/4 times 2 1/2 I'm going to get in there, right? You could see why that would be an easy mistake to make. Okay. A nice thing that you could do is just like redistribute this 1/4 and make sure it is the thing from the line before. So 1/4 times x squared is 1/4 x squared. 1/4 times -8, that'd be -8 over 4, which is -2. If you did 1/4 times 1/2, you'd get 1/8. All right. Okay, what number completes the square? 16. Half of -8 is -4. Square root is 16. Notice that when I put my plus 16 in there, it is part of the perfect square trinomial, which is protected by parentheses. So even though it looks like x squared and negative 8x, that's not what these things really are. This is really 1/4 x squared and negative 2x. This is not really 16. It's plus 4. So if you factor something out, even if you had a negative there, then you wouldn't be adding it, you'd be subtracting it from that side. So we're really adding 4, which means on the other side I should also add 4. So just be really careful. If you factor something out, then you have to distribute it before you add to the other side. Finish it up. F of x, this is plus 16 equals 1/4. X will be my first term here. It's what's half of the middle term. What's the square root of the last term? 4, because the middle term is negative, it should be negative 4. And then move my term to the other side. Some people may do this in one step. And there's a minus 16. Okay. Now, if you were doing it Dylan's method, you would have multiplied both sides by 4. You'd still have like a 4 in front of your f of x, so you have to divide by 4. Okay. You have to be careful with your order of operations there and make sure that you are applying to all things so you don't get a wrong answer. Okay. Do you want to do another one, or are you feeling good? Good? Okay. The third example that I had fractions as h and k. So, like, don't be alarmed. It doesn't have to come out nice. If you were to move the 1 to the other side and factor out factor out the 2, when you factor 2 out of the 1x, you're going to get a 1/2. Then you have to complete the square with 1/2. So you take half of a half, which is 1/4. You square it, 1/4 times 1/4, 1/16. Okay, and then you work with that number. You're not really adding 1/16 because you factored out 2. You're adding 1/8. Okay. I'll put a hard copy of that solution on my notes online. So if you get to any on the homework that have fractions and you don't know what to do, you could go look at that one as an example. There is one other problem, though, that I do want to just real quick talk about, because some people don't like it when their teacher gives them homework that has problems that aren't like the ones they did in class. And I do that a lot, but today I'm going to talk about this one. Okay. So you did this last year in Algebra 2. Write this standard form equation, which you would have called vertex form last year, given a vertex and a point. So key here is when you get a vertex, that's going to be your HN. K. When you get a point, that's your x and y, and then it's substitution. Y equals a times x minus h squared plus k. So y is 0, a we don't know, x is -1, minus -2, minus 2. And then on that side where all that stuff is happening, just work that out. Order of operations. So like you should do the thing in parentheses first. -1 plus 2 would be 1. So that's a times 1 squared minus 2. 1 squared is 1. So that's 1a minus 2. And then add 2 to both sides. A is 2. And so you can take this A with your h and k and write the equation. Y equals 2 times x plus 2 quantity squared minus 2. I'll leave that up while I'm passing back the test in case you want to copy that down into your notebook right now.